Hello everyone, this talk is on enabling reproducible and agile full system simulation. This work is by me, Bobby Bruce, with a variety of collaborators, most of whom are at University of California, Davis, apart from Matthew Sinclair and Kyle Rorty, who are at the University of Wisconsin-Madison. Matthew Sinclair also has affiliations with AMD Research. To jump straight in, our work concerned itself with the Gem 5 computer architecture simulator. The problem is a user interacts with Gem 5 to produce an architectural simulation, and from this, results are obtained, and the user analyzes this data, and then makes decisions on that data, normally tweaking their design and seeing the results of those designs. So this goes around in an iterative manner, normally many times. The problem with this is how do we manage this information? Gem 5 is simply a command line executable. It does not provide any resources to allow you to manage the output in a structured manner. If you're going around many times, you need to map which configurations were used to obtain what results. In a similar vein, how do you reproduce what you've already done? For a particular set of results, how do you go back and execute what you executed before to obtain the same results again? Again, this is left completely up to the user to build their own frameworks to manage this. Again, how do we communicate this setup in a standardized way? How do we expose this to the outside world and say, here's what I ran and here's the results I obtained? You're free to publish your results, but how could someone recreate your results? This also has a problem in that the inputs for example, a full system simulation require things like disk images. How do we communicate how the disk image was created so an end user can do exactly the same thing again? It's an error-prone endeavor. To get to the root of it, if you're doing a non-trivial amount of iterations, you might ask yourself, wait, what did I do at iteration X again? How can I reproduce it? Again, at present, a user just needs to write their own script and manage their own data. An example of a complexity that can be involved with running Gem 5. Here's a workflow of a typical full system execution in Gem 5. You require the gathering of things such as Linux kernels, which you have to then add an operating system such as Ubuntu 2004. If you wanted to benchmark, you're going to have to get a benchmark source and compile it with a particular compiler. You need to specify your system configuration via a Python script. You're going to get your Gem 5 binary, which version did you use? And even with all this, once you've executed the simulation, you're going to have the benchmark output and a whole set of stats to go through. Gem 5 provides hundreds of statistics to analyze after a typical execution. So just managing all this and logging it in a structured way is a huge effort. For most experiments, you simply have too many configurations. You have too many results. There's no standardized way to communicate these setups or allow for a reproducibility of these setups. And there's no official source for these components. For example, if you're benchmarking using Parsec, you're going to need to create a disk image containing the Parsec benchmark suite. You have to create this yourself. There's no off-the-shelf disk image available. And that's why we created this two-part solution. The first part is Gem 5 Art. Gem 5 Art is the Gem 5 artifacts, reproducibility, and testing framework. Artifacts, as in everything you use for a particular execution, is stored as an artifact inside a database. Reproducibility in this database is available to the wider world and allows this to be reproduced as all the artifacts are logged within this database. Testing in this framework allows for scalability of Gem 5 executions. It allows for Gem 5 to be run many times with different configurations with everything logged and easily analyzable. This allows for testing of hundreds, if not thousands, of Gem 5 runs. We also provide Gem 5 resources. Gem 5 resources is a set of pre-built Gem 5 compatible, open source, extendable resources. To go to our example, A typical Gem 5 resource will be a disk image containing a particular benchmark suite, which can be easily downloaded and run with Gem 5. As a high-level overview of Gem 5 art, a user will start with everything that they need for a particular run of Gem 5, such as a system configuration, a Linux kernel, a Gem 5 binary, and a disk image. To interact with Gem 5 art, they first register all these inputs as artifacts inside a MongoDB database. So for instance, an artifact in the database in this instance would be the Linux kernel, which is specify what versions were used and where this was obtained. The user would then specify a run, which consists of artifacts. The run is then executed on Gem 5, and the results of the Gem 5 execution are stored as artifacts in the database. This database may be then exposed to the outside world. A user can then query this database to see what runs were executed and what artifacts that run consists of and what the results obtained were. They can then easily reproduce these results as the artifacts and the sources of these artifacts are properly logged. To give a slightly lower level view, a Gem 5 user would interact with Gem 5 art via Python and would really come in two parts. The first is registering these artifacts, which is done via the register artifact function. In this example, the user is registering a Gem 5 binary. So there's the command for building the Gem 5 binary. There is where it exists on the local file system. There is documentation, and there's also inputs. Inputs are simply the dependencies needed for that artifact. So in this example, the Gem 5 repo is needed for the Gem 5 binary, as the Gem 5 binary is built from the Gem 5 source code. The user would then run a Gem 5 art run function. This example here is the create full system run. So if you want to run a full system simulation of Gem 5, you would execute this function, specifying which artifacts you're using, such as the Gem 5 binary, the Gem 5 artifact, the Linux binary, the disk image, and various others, as well as parameters such as timeout information. This would then log a run object inside the database, which can then be executed on Gem 5, and the results stored back in the database. Gem 5 resources is slightly simpler architecture. Gem 5 resources consists of a repository. This repository contains the source code for all the resources and instructions on how to build them. Gem 5 resources also consist of these pre-built resources built on these sources stored on our Google Cloud infrastructure. Important thing to note here is Gem 5 resources is tagged in sync with the releases of Gem 5. So if you're working with Gem 5 version 20.1, you can check out version 20.1 of the Gem 5 resources repository and obtain resources that are compatible with that version of Gem 5. So for instance, if you need a Linux kernel binary, you can go to the repository and build it yourself, or you can pull the binary from the pre-built resources on our Google Cloud infrastructure, which is simply a basic download. Time of writing, we have at least 16 apps, benchmarks, and images for full system mode, and many others for bare metal testing and GPU simulations. We're continuing to expand this with more benchmarks and more tests and more executables as time goes on. And for each release of Gem 5, we ensure that all these benchmarks, apps, and images are compatible with the latest release of Gem 5 and tagged appropriately. We're going to go over two use cases here. In our paper, we highlight three and in much greater detail. But we're going to highlight two here as they show quite clearly how Gem 5 art and Gem 5 resources are useful for specific tasks. This first example is co-design. What we mean by co-design is observing the interaction of software and hardware and how hardware and software can change and impact performance. So as a basic co-design question, we are asking, how does execution time of parsec applications change between Ubuntu 18.04 and 20.04 for single core and 8-core CPU setups? So The parameters in this experiment are changing between the operating system, Ubuntu 18.04 and 20.04. We're jumping between 10 different benchmark applications, and we're analyzing on single core and 8 core architectural setups. And this produces a total of roughly 40 runs. And for each run, we are looking at the execution time. Without Jam5art and Jam5 resources, you'd have to write your own scripts to run this. You'd have to store them in your own database setups. You need to obtain your own disk images containing 18.04 and 20.04 operating systems and the Parsec benchmark suite. But with Jam5art, this is all much simpler. It's really just a 5-step process. The first is you obtain the Parsec benchmark from Jam5 resources, which is a disk image containing the Ubuntu operating system and the Parsec benchmark. You then register the artifacts in the database. You create a run script, and then you execute. Once execution is complete, the results will be stored in a database, and from then you can query the database for the desired results. And in this example here, we get this graph. When we run this particular experiment, the 20.04 stream cluster and swaptions data incurred a timeout. But for the rest, we can broadly see that Ubuntu 20.04 is faster, considerably faster for the 8-core setup, which we think is probably due to Ubuntu 20.04 coming with a newer version of the GCC compiler, which allows for greater CPU utilization. They were also open to the idea this might be due to using a newer version of the Linux kernel. And our second use case is testing. If you've got an architectural design, you're going to need to test it, and you're going to test it a lot. That is, lots of runs of Jam5. And also, within the Jam5 project, for a release of Jam5, we want to make sure that there's no bugs, so we also test a lot, using a variety of architectural setups. So this question, we're asking, how does Jam5 perform in booting Linux on different architectural setups? As I said, this is a very common test in Jam5, but also it's a common test for users as well. So there's a lot of parameters here. We test across 5 different kernels, 1 CPU, 2 CPU, 4 CPUs, and 8 CPUs. We test on 4 different CPU models, 3 different memory systems, and essentially 2 different types of this test, booting the kernel only or booting the full Ubuntu operating system. The cross product of this makes for 880 runs, and for each of these runs we want to check whether there's success, there is an error in Jam5, or whether there's a kernel panic. I hope you can appreciate at this stage that trying to do this yourself with just the Jam5 executable will be difficult. Even just getting all the kernels you need and creating a disk image that will boot the kernel or boot Ubuntu is difficult. You'd have to just create this yourself. It would take hours, if not days, to do. And then you'd have to write scripts to manage all this setup and run and log all the data in a way that you can query later. But with Jam5art, Jam5 resources, the process is just like use case 1. You download the resources you need from Jam5 resources, in this case the kernels and the disk images, and then you register these artifacts inside the database, you create your run script, and then you execute. And then when complete, all the data is in the database, you query the database and get the results. And in this case, this is the results we get. I won't go over this all in huge amount of data, but this is just a very simple visualization that sees the status of Jam5 for every single configuration we discussed. As you can see, there's a lot of data points, but once this is running, you don't have to think about anything. It's all automated. So that concludes our presentation. We would like to thank everyone involved in this project. Special thanks to the NSF for funding this research. An artifact of this research is publicly available. We hope that you jump in and start using Jam5art and Jam5 resources for your own work. We in the Jam5 project are going to continue to improve Jam5art and continue adding and expanding Jam5 resources. Thank you very much for listening, and we look forward to seeing you at the conference.